Hello. In this lecture, I will go over some basic topics in linear algebra. If you are already familiar with these topics, feel free to skip. I will go over some basic definitions: scalar, vector, matrix, span, range, and then we go to matrix inverse. The reference is the chapters 2.1 to 2.6 from the deep learning book. And if you need a little bit more detail and if you feel these topics that I will talk are not completely accessible, then you can also look at this book. Both of these books are available in the public domain for free. Okay. So in linear algebra, there are several types of mathematical objects involved. Scalars, which is just a single number, and for example, S is a real number because we use R to indicate real numbers. We have vectors. Vector is an array of number, and typically when we refer to vectors, we refer to column vectors. So it's an array which has n, in this case, n rows, one column, okay, and has n entries. Now, matrix is a 2D array of number, and each entry is identified by two indices, which is the row and the column. And this is the first row, this is the second row, this is the mth row. This is the first column, second column, nth column. This is an m by n matrix. So the ith column of A is a vector with m entries, because this matrix A is made out of m rows, and the ith column consists of A1i, A2i, A3i to AMI. The jth row, on the other hand, is somewhere here, and it's a row vector as opposed to a column vector, and the first index indicates the row, the second index indicates the column, so AJ1, AJ2, AJN. And one important operation on matrices is the transpose. The transpose of a matrix is the mirror image of the matrix across the diagonal line. So this is diagonal line, more or less, and then imagine you switch A12 with A21, A1N. Essentially, this is what it is. So A transpose is a matrix such that the ijth entry of A transpose is the ji entry of A. So the ith row and the jth column, the entry that resides there in A transpose, resides in the jth row and the ith column of A. The transpose of a transpose is the matrix itself. The transpose of a column vector gives you a row vector. One of the most important operations involving matrices is multiplication of two matrices. Matrix product of matrices A and B is the third matrix C. And in order for this product to be defined, A must have the same number of columns as B has rows. A has n columns, B has n rows. Now, A has m rows, and we call the first row A1 transpose. Why is it a transpose? Because a vector for us is a column vector. So A transpose becomes a row vector. First row, second row, mth row. B, first column, second column, pth column. Why do we care about the rows and the columns of B? Because we want to talk about A, B. What is AB? C is AB. This is A. This is B. And then the matrix product of matrices A and B is the third matrix with entries that consist of inner products between the rows and the columns. So the first entry is A1 transpose B1. Second entry of the first row is A1 transpose B2, and then you go to A1 transpose BP. The mth row here is AM transpose, and the inner product is AM transpose B1, AM transpose B2 to AM transpose BP. So, in a way, the entries of C are nothing but the inner product of the rows of A and the columns of B. Now, what is the inner product, which we also call the dot product between two vectors? Let's say x and y. X transpose is a transpose of this column vector becomes a row vector, and y remains as it is. So in order to calculate that, we have to multiply x1 by y1, x2, y2 to xn, yn. So we get x1, y1 plus x2, y2 plus xn, yn, and this is a scalar. The inner product of two matrices, two vectors, is a scalar, and which is what's happening here. This is a scalar, this is a scalar, these are the entries of C. Some basic useful properties. matrix multiplication is distributive in the sense that A times B plus C is AB plus AC. It is also associative in the sense that A times BC is the same as AB times C. Now, AB is not the same as BA. But when it comes to the dot product between vectors, X transpose Y is the same as Y transpose X. AB transpose is B transpose A transpose. And X transpose Y, because it's a scalar, the transpose of a scalar is the scalar itself. So this is equal to the transpose. And what is the transpose here? What is this? So we can call this or A here, and Y will be or B. So B transpose will be Y transpose, and A is X transpose. So A transpose is the transpose of X transpose, which will be X. So that's why X transpose Y is Y transpose X. Now, system of linear equations. Here is an example where we have two unknowns, x1 and x2, and two equations. In a sense, we are given a11, a12, a21, a22, b1 and b2, and we want to solve that for x1 and x2, and we can write this in the matrix notation. This equation is the same as this. Now this is two equations, two unknowns. It's a toy example. More generally, systems of linear equations can be written in this compact matrix vector format, where A is a matrix, X is a vector, which is unknown, and B is another vector, which is known. In this case, this is our A, this is our X, and this is our B. Now, recall that here we call the rows of A little lowercase a, right? Here we are doing the same thing. So it's the first row, second row, mth row. X has n entries and B has m entries. So how many equations do we have here? How many unknowns? If we are talking about this equation. Well, the number of unknowns is n. We have n unknowns, x1 to xn. How many equations do we have? Well, each row of A leads to one equation. So we have m equations, n unknowns. So AXB is essentially this system of linear equations. A1 transpose X is B1, A2 transpose X is B2, AM transpose X is BM. M equations, n unknowns. Matrix inversion is an operation that allows us to analytically solve AX equal B for many matrices A. And before we get into it, let me introduce to you the identity matrix. I sub n, meaning that this is an n by n identity matrix, which means that the diagonal elements are 1, the off-diagonal ones are 0, so that any vector multiplied or transformed by this matrix Ix is X itself. Now, matrix inverse of A is denoted by A to the power of -1. And let me just say it, that this inverse may not exist for every matrix, but if it exists, it is such that if you multiply it by the matrix itself, you get identity. And why is that useful? Because to solve this equation, we can multiply A minus 1 to both sides. So A minus 1 times A is identity. A minus 1 times B, this is itself a matrix. And then you multiply it by B. And you get another vector. So you can solve it. And you get X is equal to A minus B. So, and this is all assuming it is possible to find A inverse. There are conditions that need to be satisfied for this matrix to exist. And what are those conditions? Before we get into it, let me just say a few words about finding A inverse. When A inverse exists, then there are many algorithms for finding it. And typically, calculating the inverse of a big matrix tends to be a very computationally expensive operation. So, in real life, we like to avoid explicitly calculating it, which doesn't mean that we are trying to avoid solving such equations, because the bottleneck of almost not any, I can say, let's just say many fitting procedures, the bottleneck at the heart of this procedure library function, for example, when you run a linear regression or a logistic regression or a Poisson regression, and you're fitting a model, fitting that model involves solving such linear equations multiple times. And the dimensionality, the size of this matrix A typically is proportional to typically is actually equal to the number of features, but it can be bigger. But essentially, it's the number of features that determine the size of A. But that's, I mean, what I just said, this is all very vague, because I haven't really made it, explicit, and we will do that later. For now, just all you need to know is that what a matrix inverse is, and if it exists, why can we use it to solve this linear equation? That's all. Now, what are the conditions for the existence of A inverse? We'll talk about that next. But before that, Let's look at a few statements. A inverse exists if AXB has exactly one solution for every value of B. So if for every value of B there is an X such that AX is equal to B, then A inverse exists. Now it is possible for AX equal B to have no solution. It is also possible for AX equal B to have infinitely many solutions. So this system of linear equations, this part, or what we just wrote here, is the same thing, falls into one of these categories. Either A inverse exists and then AX equal B has exactly one solution for every B, or this AX equal B doesn't have any solution, or AX equal B, it's possible for it to have infinitely many solutions. And why is it infinitely? Why is it not 2? Why is it not 3? Well, here's the thing. It's either no solution or one solution or infinitely many solutions. Why? Imagine AX equal B. There are two solutions for it, X and Y. Well, if X and Y are two solutions, meaning that AX is equal to B and AY is equal to B, then any sort of combination of them in this form, where you multiply alpha by X, where alpha is a scalar, a real number, plus 1 minus alpha times Y, if you add these two, you get a new vector, and that vector is also a solution. And since this is a solution for any alpha, and since alpha can be any number, any real number, there are infinitely many z's. Now, why is z a solution? Just check it, plug it in. Az is a times alpha x plus 1 minus alpha y, and then alpha is a real number if it's scalar, so you can take it out. So you have alpha ax plus 1 minus alpha ay. Since x and y are solutions, therefore ax is b and ay is b. So you have alpha b plus 1 minus alpha b gives you b. Therefore z is also a solution for that equation. And since z can take infinitely many different values depending on what alpha is, therefore there are infinitely many solutions for a particular b. Okay. Now, what we did here is it is an example of what is known to be a linear combination. A linear combination of x and y. Now let's look at this equation ax equals b in a different way. So far, we have explicitly had defined the rows of A. Now let's just look at A in terms of its columns. It has n columns. It had m rows, but here we talk about, we look at A through the lens of looking at the columns. and we call the first column phi1, the second column phi2, and the end column phi n. So phi I is the ith column of A. So AX is nothing but x1 phi1 plus x2 phi2 to xn phi n. Well, x is a vector. x1 is the first entry of this vector. x2 is the second entry of x. So x1, x2, and xn each are scalars. Phi1, phi2, and phi n, each of them is a vector. So here we are dealing again with the linear combination of the vectors, phi1 to phi n. So AX is essentially a linear combination of the columns of A. This is basically an illustration of what I just said. So imagine this is a two-dimensional space. This is phi1, phi2. So 2 phi1 plus phi2 is just, this is 1 phi1, then you add another phi1 here, and then from here to here you go to phi2, and then from here to here you get 2 phi1 plus phi2, which is essentially what I'm doing here. Okay. Let's come back to the original questions. How many solutions AX equal B has? It's either no solution, or only one solution, or infinitely many solutions. Now, in order to answer that question, I like to introduce a very important concept: the span. The span of a set of vectors is the set of all points obtained by linear combination of the original vectors. So this is a linear combination of these phi1 to phi n. So the span of phi1, phi2, phi3 to phi n is essentially all the points that we can get by having this linear combination with various values for x1, x2 to xn. Okay. So coming back to the original question, does AX equal B has a solution? The answer is essentially B has to be in the span of the columns of A. In other words, it should be possible. So, in other words, AX equal B has a solution as long as these columns their linear combination. A linear combination can be found such that it's equal to B, or in other words, B is in the span of the columns of A. Now, the span of the columns of A, there is another way of referring to it too, which is called the column space of A, or the range of A. In other words, what are the points we can get by having AX? So for AX equal B, to have a solution, B must be in the span, it must be in the column space of A. Now for AX equal B to have a solution for any value of B, since B can be any point in the space, therefore the column space of A should be all Rm. Because if it wouldn't be all Rm, it means that there is a point in Rm which we cannot obtain by having AX. Now, for the column space of A to be all of Rm, the number of columns must be at least m. In other words, n should be greater or equal than m, because n is the number of columns of A. Now, this statement and many other statements I mentioned earlier, they have rigorous proofs. And if you look into, for example, this book in particular, then you can find a proof for any of the statements, and the proofs are not so technical in the sense that they typically just are a few lines, and if you know the basics, then you can follow them. And I encourage you to spend time on your own to go over them. Now, for the purposes of this class, since we are just reviewing linear algebra, I will not go into the proofs. But that doesn't mean that the proofs are not important. It just belongs to a different place and time and class. Okay, coming back to our linear equation, and you may say, why are we spending so much time on linear equation? And I have to say, this is the computational bottleneck of a lot of machine learning algorithms, a lot of statistical methodologies. You can think about it this way. I mean, even though I have not defined it clearly, but when you're doing linear regression, you are, or the computer is essentially solving such an equation where B depends on the observations, A depends on the observations, and X is our coefficient of the predictors. Now, coming back to this equation, this is an equation where we have m equations, n unknowns, and we just said that the column space of for the column space of A to be all Rm, then we need to have at least m columns. Now that's a necessary condition for Ax to have a solution for every Rm. Why do we need this? Again, for a rigorous proof, I refer you to the book. For the intuition into it, just think about it. If you are in a three-dimensional space and you only have two vectors, these two vectors in a three-dimensional space define a plane. And a plane does not cover the whole three-dimensional space. That's an example. Now, again, having n greater or equal to m is only a necessary condition. What is the sufficient condition? That has to do with linear dependence and linear independence. And what do we mean by linear dependence or independence? This is what we mean. A set of vectors phi1, phi2 to phi n are linearly independent if and only if. Okay, so this is a typo. This should be phi1, phi2, phi n. Let me correct this. Okay, so a set of vectors phi1, phi2 to phi n are linearly independent if this holds only for alpha 1 to all 0. So what does this mean? It means that the only way that these vectors can be, that we can create a linear combination of them, essentially, because these alpha 1, alpha 2, alpha n, they are scalars. So when we add these, when we multiply these scalars by these vectors and add them up, we are creating a linear combination. And the only way this can be 0 is that all these scalars are 0. And what does that mean? It means that we cannot, for example, use phi 2 to phi n and find a linear combination between them to create phi 1. Okay? So, in other words, no vector in this set is a linear combination of the other vectors. So they're pointing in different directions, and these directions are such that no vector in the set is a linear combination of other vectors. Now, if we add a vector to the set that is a linear combination of the other vectors, this new vector does not add any points to the set's span. Why? Because that new vector is already a linear combination of the other vectors. And what is the span? The span is the set of points covered by the linear combination of these vectors. So since it's already a linear combination, there is nothing added to the span. Now, the independence dimension inequality essentially says that in an m-dimensional space, if you have n vectors, these are linearly independent only if these n vectors, the number of them, which is n, is less than equal than m. Or in other words, any collection of m plus 1 or more m-dimensional vectors is linearly dependent. So in an m-dimensional space, you can have at most m linearly independent vectors in a set. So that's it essentially. So if you're a two-dimensional space and you have three vectors, they have to be linearly dependent. If you have two vectors, they still can be linearly dependent, but they can also be linearly independent. So this means that for the column space of A, which is the columns are phi 1 to phi n, so you have n vectors in an m-dimensional space, in order for these n vectors to encompass all of Rm, the matrix must contain at least one set of linearly independent columns. M linearly independent. Why M? Because the space is M. So if you want to encompass the whole space, then we need at least M linearly independent. M rows and columns. So N should be greater or equal than M. Okay. So coming back to this linear equation, ax equal b, for this equation to have a solution for every b, that means that the column space of A must encompass all of Rm, because we're saying it for any b. A must have exactly m linearly independent columns. Okay, not at least m. So okay, so let's just summarize what we learned. The matrix A has an inverse if A is square and the columns of A are linearly independent. That means that if they are linearly independent, the columns, it turns out that the rows of A are also linearly independent. But essentially, A has an inverse if these two are satisfied. So A has to be square and the columns need to be linearly independent. And if that's the case, then this equation for sure has a solution, and it's only one solution. Now, the overdetermined scenario is when we have more equations than variables. Okay, so the variables, the x's, you can think of them as degrees of freedom that we can play around, but we have more equations, and in other words, A is a tall matrix, and the only way that the solution would exist is if B is in the span of the columns of A. So the columns of A, there should be a way to create a linear combination of the columns of A so that we can get B. And for that to happen, B must be in the span of the columns of A. Now, the underdetermined case, there are more unknowns than equations, and again, if essentially there is a solution if the span of B is in the span of A. Now, since there are more unknowns than equations, then we may have infinitely many solutions. So for square matrices, if the inverse exists, then not only A inverse is identity, but also A inverse A is identity. Norms allow us to measure the size of a vector. There are different norms, and the LP norm is defined in this way. Essentially, we write these two lines, and then we have this P, and it's the sum, absolute value to the power of P, square root 1 over P. The L2 norm is just the Euclidean distance. It's defined this way. And then if you add a 2 here, then we just get rid of the square root. L1 norm is just the sum of the absolute values. And the infinity norm is just the maximum of the absolute values. We will mostly work with these two norms, L2 norm and the L1 norm. Just some basic definitions. Diagonal matrix is a matrix where only elements in the diagonal are non-zero. So it consists mostly of zeros and non-zero entries only along the main diagonal. Symmetric matrix is a matrix that is equal to its own transpose. Orthogonal matrix is a square matrix whose rows are essentially A transpose A is equal to AA transpose is identity, implying that A inverse is A transpose. A unit vector is a vector with unit norm. That means the L2 norm of x is 1. Note that the L2 norm to the power of 2 is x transpose x. We say x and y are orthogonal to each other if x transpose y is 0. So the inner product is 0. In general, inner product looks like this. You have two vectors, x and y. There is an angle between them. And x transpose y can be written as the norm of x, which is this length, times this length, which is the norm of y, times the cosine of the angle. So in many applications, the inner product is a useful measure of similarity or dissimilarity between two vectors. Okay, so this is the first part of our linear algebra lecture, which was preliminary, but we needed to go over it so that to make sure that everybody is on the same page. Thank you.